Yeah.
Let's wait till the clock strikes 5. Are you ready, Erhard?
Sure, whenever you're ready.
Okay. All right. It is now time to start. Good morning, good afternoon, everybody, and welcome to today's seminar. Today's speaker, of course, needs no introduction. It is my exceptional pleasure to introduce Erhard Neher from the University of Ottawa, who will talk about corestriction or norm and give us an introduction. Please, Erhard.
Okay, there are some background notes. Hello. Okay. Okay, so hello, everybody. I would like to start by thanking everybody to come to this talk, and I would like to thank the organizers to give me a talk, to give me the possibilities to talk in this seminar. So my talk is a little bit outside of the usual topic covered in the seminar, and I have therefore decided to give you an introductory talk. So here's the plan. Let me change this. Okay, so I will talk about corestriction and increasing generality. I will first introduce corestriction for finite Galois extensions of fields. This is in fact the standard or the original setup in which one has defined corestriction. So this goes back to Albert, Riem, and Gille. I will then give you an extension replacing finite co-extensions by finite étale extensions. I will tell you a little bit about why I became interested or fascinated by corestriction. And this will lead then naturally to generalizations of corestriction, where the setup of finite Galois extensions or extensions of a field is replaced by a setting where the base structure is just a commutative ring, and we look at finite étale or finite projective R algebras. And in the end, I will briefly mention what one can do when what one can do over schemes. Okay, so that is the setting. Okay. So let's start. So the general setup, I have to adjust a little bit my screen, just a second. Okay, this is done. Okay. So the general setup of corestriction is that you have an object over F prime, and you want to go to an object over F. Now, there are, of course, natural constructions to do this, which have to do with descent properties. And so corestriction in the original setup is, in fact, something which I would say is an augmented Galois descent. So therefore, I will first talk a little bit, or have review what is Galois descent. Okay. So Galois descent. So we fix a finite Galois extensions of fields. So we have a Galois group, G. Then in order to cover a lot of ground, I will use a category of non-associative F-algebras called ALG, capital ALG over F, which allows base change. So admittedly, this is a little bit vague. This could be the category of just F vector spaces, so algebras have zero product. This could be the category of associative F-algebras, or this could be the category of all non-associative algebras. It could be, for the time being, just a category, also category of Lie algebras. So we take an object in this category, capital A prime, and now we can restrict the scalars from F prime to F. And then this allows me to introduce the F-linear automorphism of the F-algebra A prime, preserving the structure of alg F prime. So, for example, if we have the category of vector spaces, then this would be the category, the out F of A prime would just be the F-linear invertible automorphisms of an F prime vector space. If we have the category of associative algebras, then odd F of A prime would be the category, would be the group of F linear automorphisms of the algebra A prime. Now we want to construct a Galois descent datum, which is the following. We want to use this Galois descent datum. So it is a group homomorphism from the Galois group into the F-linear automorphism of A prime in such a way that if you map G to G prime, then G bar of F prime A prime, we know it's already F-linear, but in fact it is G semilinear. So this is what this equation here should or tells you. Okay. So we take such a group homomorphism, and then we can just look at the fixed points under this action, under this map. So A prime upper G consists of all A prime, little a prime and capital A prime, such that G bar of A prime is A prime for all G in G. And then, with these notations out of the way, here are the basic facts of Galois descent. Namely, you can start with an algebra A downstairs over F. You can move it up to F prime by taking base change, by associating to A prime, which is F prime over F tensor product over A, right? Now this has a canonical descent datum, namely for a G in my Galois group, I define G bar of F prime over A by just letting it act the G on the first component. It's G of F prime. And then it's easily seen from basic facts of Galois theory that F prime over F times A, and then taking the G invariance, is isomorphic to A. Conversely, if I start with an object over F prime, which has a descent datum, then I can look at my fixed point subalgebra, and it turns out that this is in algebra over F. This is due to the fact that the maps, that delta lands in the automorphism group of A prime. And if I now take the base change F prime up from A prime over G, I get back my A prime. And so what this tells you is that there exists an equivalence of categories. On the one hand side, we have objects over F, we have our alg F, and on the other side, we have alg over F prime, whose objects are objects in alg F prime, which have descent data. Okay. Of course, in general, an object in the category alg F prime need not have descent data. Now, in order to define corestriction, we use some trick. Namely, the general idea is to go, well, the general goal is, let me recall, to go from alg F prime using corestriction to alg F. So how do we do this? Well, the trick is that we move from alg F prime to the subcategory of alg F prime with descent data. And then we use Galois descent to get to alg F prime, to get to alg F. Okay, so in order that this works, I need to assume that my category I'm considering has not only base change, but allows tensor products, right? So for example, if this alg F prime consists just of F prime vector spaces, then this is no problem. If it consists of associative algebras, then there's again no problem. However, if you started out with Lie algebras, then the tensor product of Lie algebras is in general not a Lie algebra, so you're out of luck. On the other side, if you just use all non-associative algebras, then this will work. Okay, so that is to start with an object in alg F prime, A prime, increase this object so that it has a Galois descent datum, and then use Galois descent. So how do we increase the object? Well, let G be an element of your Galois group. So we define a new object in alg F over F prime, which I denote by AG, A prime upper G, lower G. And this object is essentially the same as our original A prime. It differs only by the scalar multiplication from F prime. Namely, we define A prime by overlap upper lower G by saying there should be an isomorphism or from A prime to A prime lower G by simply taking an element A prime and putting an index G. And then we say this should be an F-algebra isomorphism, right? So this means the sums are preserved, products are preserved if you have products. So this is an F-algebra isomorphism, and we change a little bit the F prime action, right? By saying that if I have an element of my field F prime, it should act on H A prime lower G by the following rule. I first apply G inverse, G from my Galois group, to F prime, then I have the standard F prime action on A prime, and then I move this element to A prime lower G, right? So I have the nice formula that F prime times A prime lower G is just G of F prime times A prime G. And then this gives me a descent datum of the tensor product algebra, A prime G, tensor over all factors. The factors are indexed by the elements of the Galois group, and the tensor product is the tensor product over F prime. And this has a descent datum, namely, in the most natural way, I move a factor A prime H to A prime GH just by changing the index. And then I define the corestriction by saying, let's take the tensor product over all A prime G. This now has a Galois descent datum, and I take the G tensor G fixed points. So that it is, this is corestriction. And it's easily seen. It's not only goes on the objects or in our category, but it's in fact a functor, which it preserves the natural morphisms. So we have a functor from the category alg F prime to the category alg F, mapping A prime to the corestriction of A prime. So let me give you a quick example. Suppose our Galois extension has degree 2. So our Galois group has two elements, the identity and a non-trivial element, which I call kappa. I take an F prime algebra A prime. I define A prime kappa by putting an index kappa on all elements of A prime. I define operations by saying A prime kappa plus B prime kappa should just be the sum A prime plus B prime, and then taking kappa. If I have a product, I use a similar form for products, and I say I define the right-hand side, I've defined the F prime action for the kappa algebra by this formula here. F prime A prime index kappa is kappa F prime times A prime. Then the Galois action is given, the Galois descent datum is given by the switch map. If I have a map from A prime tensor over F prime is A prime kappa to itself, which is obtained by taking a simple tensor, A prime, B prime kappa, and then just switch the factors. Right, so this is what it is, what then the descent datum is in this particular setup, in this particular example, and then the corestriction for degree 2 extensions is a subspace or a subalgebra if you have algebras, which is defined by taking the fixed points under the switch map. Okay, so what properties does this corestriction have? Why is it of importance? So here is a rundown of some useful properties. First of all, well, if you have an this F prime vector space V prime, then of course the corestriction will be an F vector space, but you can calculate its dimension, namely the dimension over F of the corestriction of this vector space F prime is just the dimension of V prime over F prime to the power D. Right, so for example, this tells you that the corestriction of the vector space F prime is F. Another important property is that we can look at an associative, or we can look at associative F prime algebras, then the corestriction will be an associative F algebra. We can look at unital F prime algebras, the corestriction will be a unital F algebra. Now, the corestriction of an endomorphism algebra of endomorphisms of the vector space V prime over F prime, this is canonical isomorphic to the endomorphism algebra of the corestriction of the vector space V prime. And now, of course, the endomorphisms of V prime over F prime are special cases of central simple algebras, so this leads me naturally to central simple algebras. So recall that central simple F-algebra is an algebra which is associative, unital, central, meaning the center is one-dimensional. It is simple, and it has finite dimension. Then from property 3, rather, it is not difficult to see that if you take the corestriction of a central simple algebra, it will be a central simple algebra again. So corestriction preserves central simple algebras. Corestriction preserves tensor product of central simple F prime algebras. And corestriction preserves Brouwer equivalence. So we get a map from the Brouwer group of F prime to the Brouwer group of F by taking the corestriction. Now, a very nice property of the corestriction is the following. You can start over F, take a central simple F algebra, move up to F prime by taking the tensor product with F prime. So I get a central simple F prime algebra, which is usually called the restriction of A with respect to F prime over F. But then I have a map from the Brouwer group of F prime to F. So we can move from the Brouwer group of F prime down to the Brouwer group of F. And this gives us a map, composition of the restriction and the corestriction, gives us a group homomorphism from the Brouwer group of F to the Brouwer group of F itself. And what it is it's just the D's power map, where if you assume, which I hope I said somewhere, that F prime over F is degree D. So the D's power map in the Brouwer group, recall, is just given by taking default tensor products. Okay. So this is sort of a short review of what is known in the classical theory, where one considers corestriction over fields. Now, there is a straightforward, essentially, extension where Galois extensions are replaced by finite étale extensions. So let me give you some details about that. Okay, so this was promoted by Riem in the 70s. There's also work of Scharlau, and it's used by Tignol. So what we do is we still have our field F. We replace the Galois field F prime by a commutative associative unital F algebra, which is finite étale, which I recall means the following. F prime is just a direct product algebra of factors k1 up to kn, and the ki over F are finite separable field extensions. Okay. So this is the usual definition of a finite étale F algebra. there exists an equivalent definition which is more useful to my purposes, namely, there exists a finite Galois extension L over F, such that if you look at the tensor product algebra F prime over F is L, then this is just the direct product of L with itself, enough factors, namely just the dimension. The number of factors is just the dimension of F prime over F. Now, we can then easily modify the corestriction construction as follows. So, as before, we take an A prime in our category of objects over F prime. Now, previously, we had a Galois element, a Galois group element, which I used to change the scalar multiplication. Now I will use an X in the homomorphisms of F algebras, in the homomorphisms from which go from F prime to L. And instead of defining a new algebra over F prime, namely, I say the action of L on the new algebra A prime over X, the L action should be given by this formula here. We call that X is invertible, so L times A prime index X is X inverse of L times A prime, right? So this then gives me an algebra over L. As in the Galois case, I will just take the tensor product over all x's. I have a canonical Galois descent datum and on L, and I define the corestriction in the finite étale setting by using the fixed points under the Galois action on this tensor product algebra A prime over X, over all X in X. So here's a short comparison. As you can see, does not seem to be a lot which has changed. In the Galois case, F prime equals F. The Galois group is the same as X. The corestriction is the fixed point under the Galois group. In the finite étale extension, I have two extensions. I have F prime and I have L. I have the Galois group. No, I have the Galois group from L over F, and I have the homomorphisms from F prime to L, and the corestriction follows the same formula, and so it's not surprising that essentially all properties which I mentioned before generalize from the Galois case to the finite étale case. So here's an example which should also tell you that, yeah, we gain something more, namely a very nice étale extension. An important étale extension is the so-called split extension. Namely, we can just take the direct product of d factors of our field F. Right, so of course then F prime is no longer a field. But still, it is a finite étale algebra because it is already split. So in this example, our L, which we had, the setting, the general setting here. So this L here, this L now can be taken as the base field F. The Galois group then is just a trivial group. And the homomorphisms, the F-algebra homomorphisms from the split finite étale extension to L are just the projection maps. You project from factor F to itself. Now, if you take an algebra A prime in our category algf prime, say in the category of vector spaces, then this is the same as a direct product of with factors A1 up to AD, where AD are in the algebra over F. So if we consider associative algebras over F prime being the split finite étale extension, then any object, any associative F prime algebra is just a direct product of the associative F algebras. Now, it's easily seen that my twisted version of A prime with respect to the homomorphism, the projection on the ith vector, this is just the vector AI. And so, using the general formula, what happens is that the corestriction of F prime over F is of the direct product algebra is just the tensor products of the corresponding algebra. So it's multiplicative in a very natural sense. Okay. So now let me tell you why I got fascinated with corestriction. And this has to do with the exceptional isomorphism of Dynkin diagrams. A1 times A1 is isomorphic to D2, right? So here it is. A1 times A1 is D2, and you can't see the full D2, but this vertical points are just the end of the Dynkin diagram of type D. Now, whenever you have a category whose isomorphism classes are given by Dynkin diagrams, by the isomorphism classes of Dynkin diagrams, then this exceptional isomorphism then will tell you, yes, there must exist an isomorphism of the object. So, for example, this works for semi-simple Lie algebras over algebraically closed fields of characteristic 0. SL2 times SL2 is isomorphic to SO4. But it also works for adjoint algebraic groups. PGL2 over an algebraically closed field K, PGL2 over K times PGL2 over K is isomorphic to PGO plus over K. This is the notation of the Book of Involution. Of course, I mean, one can, of course, write down a concrete isomorphism of these algebraic groups. Now, the magic of stacks will tell you that there are 4 categories which become equivalent, which are equivalent. Here they are, these 4 categories. So the first category is denoted A1 upper 2, and its objects are pairs consisting of a finite étale extension of degree 2, F prime over F, and a quaternion F prime algebra. So F prime over F being étale of degree 2, of course, just means that F prime over F is either Galois or it is the split étale extension. And the morphisms are F-algebra isomorphisms. The group version of these categories are semi-simple adjoint algebraic groups G over F, which are of type A1 upper 2. So that means that if I take my algebraic group over F and take the base change to F bar, what I get is a direct product of PGL2 of F bar times PGL2 of F bar. And the morphism in these categories, I take the F isomorphisms of algebraic groups. So the D2 category has objects triples, A sigma F. So A is a central simple F-algebra, which has rank 4, degree 4. So that means over the base field F, its dimension is 16. The sigma is a special type of involution of first kind, so it fixes the center and it has a certain fixed point subalgebra with a certain, which is, it's called an orthogonal involution. The little f is what is called a semi-trace. This is something which you only need in characteristic 2, so for most practical purposes, we forget about it. And the morphisms are F-algebra isomorphisms. And then we have the group version of the category D2, namely the objects are semi-simple adjoint algebraic groups over F, which are of type D2, meaning that if you take your group, you move it up to the algebraic closure, what you get is PGO plus of G. So stacks will tell you that, or the stacks which sit behind these categories will tell you they are all equivalent. But of course, there are concrete isomorphisms, and you can see a very concrete isomorphism in the book of involutions, and this is where corestriction comes into place. Namely, the category A1 up to 2 is equivalent to the category D2 by taking a pair F prime over F to Q prime. And what you do is you map it to the corestriction algebra, corestriction of F prime of Q prime. Then the orthogonal involution is obtained by taking the corestriction of the canonical involution of your quaternion algebra. And, well, there's a way to take a corestriction of a semi-trace. Now, this is so far so good. And now you look at this category and I told myself, well, gee, these categories of groups over F, over fields F, they make sense by looking at algebraic groups over schemes, right? There is a well-defined notion of a semi-simple adjoint algebraic group over a scheme S, and there is a well-defined notion of a semi-simple algebraic group of type A12. There exist well-defined notions of semi-simple adjoint algebraic groups of type D2 over scheme. And it's equally true that you can easily imagine what is the scheme version of our category A1, 2, and D2. So this category exists over schemes. And so I asked myself, and my collaborators asked with me, is there are they equivalent, and is there a generalization of corestriction which will give us the equivalence of the generalized categories? Now, before I tell you more about the generalizations of corestriction, let me give you a quick example of the equivalence of the category A1, 2, and D2 for the special case where the base field F is R. I think this is very useful. Okay, so if I take as a base field F the real numbers, so A1, 2 has objects F prime over R and Q prime. So F prime over R is étale. Oh, I forgot to write it down. So F prime over R has degree 2. So there are only two cases. F prime could either be the field of complex numbers, or F prime is R cross R. Now, if F prime is R cross R, the quaternion algebra over F prime is just the product of two quaternion R algebras. On the other side, the objects in the category D2 are now pairs A, sigma, where A is a central simple R algebra of dimension 16. Sigma is an orthogonal involution. So how does this equivalence look like? I will give you just how the corestriction works in this setup. Okay. So now there are up to isomorphisms for objects in the category A1, 2. Namely, if F prime is just the Galois field extension C over R, there exists only one quaternion algebra of the complex numbers, namely the 2x2 matrices, which I view as the endomorphisms over C of the two-dimensional vector space C2. Now, by one of the rules I told you, the corestriction will map this into the endomorphisms over R of R4, which is 4x4 matrices. Similar, next case, if F prime is R cross R, well, there are two types of quaternion algebras over R up to isomorphism. It's either the split quaternion, which are 2x2 matrices over R, or it's the division quaternions, namely the Hamiltonians. And so we get three objects. We map under the corestriction mat to R times mat to R, we map this into the tensor product, right? And this is, of course, just 4x4 matrices over R. The Hamiltonians cross the Hamiltonians are mapped into the tensor product of the Hamiltonians, which is again mat for R. And if I have the mixed case, the 2x2 matrices over R times the Hamiltonians, then this is mapped onto the tensor product, which gives us the 2x2 matrices over the Hamiltonians. So you see, well, we get at least all two central simple algebras over R of dimension 16, namely 4x4 matrices over R and 2x2 matrices over the quaternions. Now I claimed that this is in fact an equivalence of categories. And yes, it is an equivalence because there are three isomorphism classes of orthogonal involutions on the 4x4 matrices over R. Okay, so now let's move on to generalizations. As it's still on, as you can see, I'm interested in generalizing all of this to a setup where the base field F is replaced, say, by a ring R, or by even something more general, by a scheme. Now, it's not so out of the world to think that there must be generalization. Namely, there have been previous people who have done this. Okay, so first I should mention already in 1962, Grothendieck looked at generalizations of corestriction, and he called these generalizations the norm. And so the corestriction in a general setup changes its name. It is now called the norm. And he looked at finite locally free morphisms of schemes, So for example, if S prime and S is affines, then this means just that you have a map from the spec R prime to the spec of R, where R prime is finite projective as an R module. Now, in the setup which I explained before of Galois fields, we defined the corestriction by using Galois descent. In this setup, Grothendieck defined this by using some sort of Zariski gluing. And in fact, he was interested by the Picard group of invertible OS prime modules. In fact, I should say before that this construction, which you can find in EGA, it just works for invertible OS prime modules. And so if you look at the isomorphism classes of these invertible OS prime modules, these is just the Picard group of S prime. And Grothendieck used the norm to define a group homomorphism from the Picard group of S prime to the Picard group of S. And that was his main interest. Now, there have been other generalizations which work in the affine setting, where one uses a base ring R and a commutative associative unital R algebra, which is finite projective as R module. And the goal then was to construct a functor from the category of R prime modules to the category of R modules. So this has been done in 1974 by Knus and Oyanguren, and they defined their norm, generalization of the corestriction, by replacing the Galois descent, which we used before in the Galois setup, by replacing this by faithfully flat descent. There exists a more general norm functor, which was defined by Ferrat in 1988. And he defined this norm by using some universal property, which I don't want to recall here. And alas, there is also some work by Rost, which, not surprisingly, he did not publish. It's a preprint on his website. And his definition works via so-called symmetric tensors. And he used this to define what is called a multiplicative transfer for the Witt-Grothendieck groups going from R prime to R. So the Witt-Grothendieck group of R prime maps to the Witt-Grothendieck group of R. Now, I didn't tell you the definition, but at least I would like to tell you some of the properties. So this norm in the general setup, where R is our base ring, R prime is an R algebra, which is finite projective as R module. So this norm is actually a polynomial, something which is difficult to see if you just look at fields. And it's polynomial in the following setup, in the following meaning. So take an associative commutative R algebra, then define T prime as the tensor product of R prime over R with T. This then is finite projective as a T algebra. Take a module M prime, take the tensor product over R with T. This is a T prime module. And now the norm preserves tensor products. Namely, I can first take the norm of M prime. This is on the left-hand side here. This gives me an R module. then I take the tensor product with T, gives me a T module. On the other side, on the right-hand side, I can look at M prime tensor over R with T, and I can then take the norm of this module going from T prime to T, and these two T modules are canonically isomorphic. So polynomial now means that there exists these isomorphisms which preserves maps from from the T to T prime. And this is a basic property which Ferrand used to define his construction. Now, again, we have the split case. And again, in the split case, if I take R prime as factor algebra, we have d factors of a base ring R. M prime then is just a direct product of R modules, and the norm is the tensor product as we have seen in the field case. If you have an associative, non-associative R prime algebra, there exists a canonical product on the norm. It preserves associativity. It preserves unital algebra. Now you would like to have that it preserves finite projectiveness. It preserves Atsumaya algebra, but it does in general not preserve finite projectiveness. For this, I need to go from finite projective R modules to, I need to assume that R prime is not only finite projective, that it's finite étale. And then M prime finite projective implies that the norm is finite projective. This allows then one to prove that if A prime is a Atsumaya algebra over R prime, then the norm is an Atsumaya algebra over R. From there, it's not difficult to show that the norm gives you a group homomorphism on the Brouwer group from R prime to the Brouwer group of R. And if your extension R prime over R is étale of degree D, and A is an Atsumaya R algebra, then you can play the game we have played before. I take my Atsumaya algebra over R. I move it up to R prime by taking the tensor product. I move it down to R by taking the norm, and then I take its Brouwer class. And this is the same as taking the default product, tensor product of A with itself. Now, let me finish by telling you quickly how this can be generalized. So this goes as follows. So this is joint work with Philippe Gille and Ruether, which is posted on the archive. And what we do is, so the field F was replaced by the ring R, and it's now replaced by the scheme S. We look at the big FPBF side of schemes over S. This is a side which is a ringed side. It has a structure sheaf given by taking the global section functor. This then allows us to define the category of quasi-coherent O modules over this site. And then the canonical extensions of what I have told you before over rings remain true. Namely, if S prime over S is finite locally free morphisms of schemes, we can define a norm functor from the category of quasi-coherent modules over the schemes of S primes to the quasi-coherent modules of schemes over S, which has the following property. Now, look at an affine scheme U, which maps to S, and take an quasi-coherent module over S prime. Now, you see, if you consider the global section functor, then you get a finite projective O of U algebra. Similarly, if you take your M prime, evaluate it at S prime over U, then this is an O of S prime over S U module. And so we are in the setting of Ferrand. And so the norm functor is essentially defined by defining it on the affine schemes by saying it should be the norm functor of the Ferrand norm, which Ferrand has defined before. So this is my definition for an affine U. Of course, what lies behind the theorem is that all these definitions fit together to give you a nice functor globally. And now this norm functor preserves all the properties which I told you before, where F prime is finite projective or a finite étale. So it maps you, for example, it will map Atsumaya algebras over schemes to the scheme S prime to Atsumaya algebras over the scheme S. And it does what I set out to do, namely, it gives you an equivalence from the four categories which I explained before for fields, which you can easily define over schemes, and the equivalence of the category A12 to D2 is in fact induced by the norm functor which I have defined above. Let me stop here. Thank you very much.
Thank you very much indeed, Erhard, for this beautiful talk. Let's thank the speaker. There are various technical or less technical ways of thanking the speaker. Let's open the floor for questions. Please just unmute yourself and ask a question, or write in the chat and I will read it out loud if you don't have the possibility to speak. So maybe I can start with one question, if I may. To the very beginning, when you defined the corestriction, you somehow took your object over F prime and you constructed one privileged descent datum, and this gave you an object over F. In general, if you have an object over F prime, you might have, with a descent datum, it might be a different descent datum. So is there some, is there a way to motivate why this particular descent datum is the most natural, or something like that?
Well, if you have a different descent datum, it will give you a priori different algebra over A. So in this category of alg F prime with descent data, the morphisms there are morphisms not only preserve the algebra structure of F prime, but they will also preserve in a canonical way the descent data. Right? So if you have there exists a canonical isomorphism of descent data. So then of course, if you have this object over F prime with a second descent datum over F prime, which is not isomorphic, then you will get a different object over F.
May I chime in?
Yes, please.
One of the properties Erhard pointed out is that when you have sort of split étale extensions, you get the tensor product. And this describes, well, étale extensions, but also Galois extensions locally. And if you decide that that's the property you want and you try and reverse engineer everything, you sort of have to take this descent data. So if you take a different one, you'll lose the tensor product in the split case.
I see. Right. Thanks.
It's good to have your collaborator in the audience. He can answer all the difficult questions.
Yes, I'm Einstein's driver from the joke.
Other questions or comments in the audience, please?
Well, I remember that we started doing this, as you said, because of the A1, D2 equivalence. There's also the, D3, A3. And there you also have the objects of D3 are like a higher dimension. There's some jumping going on. But I didn't look in the book of involutions. I probably could have turned one more page, but do they use a corestriction there as well?
No, I don't think so. I don't think. Yeah, I don't think that they use. I think it works with the Clifford algebra construction they use.
Ah.
Is there a really non-associative, I mean, a sort of an algebra that is not associative that you have looked at in this context, like an octonian algebra or something?
Okay, of course, I looked at octonian algebras, but it does not work. But there are generalizations of associative algebras which have recently been considered, and I think it works in using this generalizations. This is work by Vishne and his collaborators. This is very recent. So they have a setup where they have generalization of the Brouwer group. It becomes then a Brouwer monoid. And so I haven't looked at precisely in the details, but I think the corestriction will work in their setting. It will give you homomorphism from the Brouwer monoid over F prime to the Brouwer monoid of F.
Oh, interesting.
Of course, it would be interesting to see what sort of algebras arise if I take the corestriction of an octonian algebra or take the corestriction of a Jordan algebra. I'm sure these could be described in terms of certain identities. So, I mean, there must be something. A meaningful category of non-associative algebras, but it still has to be described. It still has to be discovered.
Oh,
as far as I know, nothing has been done in this setup.
I see. Further questions? If there are no more questions, let us thank Erhard very much again.
You're most welcome.
And this concludes our seminar for today. Thank you very much all for coming. See you next time.
Bye-bye.